We have a very special session this afternoon, a workshopping session designed by Delia Pembrey from the International Society for System Sciences, Fred Roberts, who's joining us from DIMACS at Rutgers, and Alexis Tsoukias from here. They're going to help us explore sustainability and human-machine collaboration. So I'm going to turn the floor over to the three of you.
Okay, well, so the idea here for our session is to introduce the concept of sustainability in human-machine collaborations. And we'd like to do this in such a way that we end up with considerable discussion and ideas for future collaborations among ourselves and our colleagues, as well as ideas for research. So we've decided among the three of us who are organizing this session, and my colleagues Dee and Alexis, that we will each present notions of sustainability from a different sector. So Dee is going to talk about brush fires, Alexis is going to talk about water, and I'm going to talk about electrical power systems. And we'll each kind of set the stage for the breakouts that we will have afterwards. And hopefully we'll find a way to engage many of you in the discussions. And then we'll get back together when the breakouts are done. So a little bit about sustainable electrical power systems. Can everybody see the second slide?
Yes.
Okay, excellent. So such systems grow and have certainly grown up haphazardly and incrementally. If we had to design our current electrical power systems from scratch, I think it's fair to say that we would have done it quite differently than we ended up. These are very complex systems. They're very large. They change constantly because loads change. There are unexpected disturbances. All kinds of stochastic events take place, weather events, changes in usage. When there's a World Cup going on, everybody's watching television, etc. So cascading failures are another factor, and they can cause extreme events such as blackouts. And so it's a very complicated system, and we face all kinds of challenges with it. The system today is managed by large parallel computers, supercomputers. The system was not set up to be managed this way. But we're dependent on those machines for reasons I'm going to explain. When it comes to sustainability, of course, we can't ever return systems to their exact prior configuration before there was a disruption. But in the case of the power grid, we'd like to come as close as possible because our experience is that if we try to make even small changes, sometimes there are disastrous consequences. So an example is the great North American blackout we had in 2003, which ranged from Canada to the United States and affected the power in a significant part of the continent. So this contrasts to what you're going to hear from Alexis and Dee about floods and fires and things of that sort. In this case, we maybe have the opportunity, as we did, for example, in the recent hurricane and flooding in Florida that we had, where there's significant debate about whether you want to rebuild on floodplains and whether instead you want to make totally different decisions about human habitation in those areas. So the challenge, though, that we face is that humans and computers, in the case of the power grid, have to interact, and they want to return the system to a relatively normal configuration without major changes. How can we do that? And why would we need to, and when would we need to? So as I said, the power grid is a massive complex system. To determine what's really happening in real time, you have to get lots and lots of information about hundreds of thousands of miles of transmission lines, for example. And you have to be able to make decisions really fast, in real time, or sometimes I say faster than real time. And I'll explain that in a minute. The power grid operator has to be able to see several moves ahead. And you have to be able to sort through millions of possible scenarios and choose an appropriate response if there is an indication that there's an anomaly. And the reality is that humans just cannot respond quickly enough or calculate fast enough to be able to do that. So that's why we have to have human-machine collaboration. And of course, as you know, machines are very good at large, complex searches. But they also have to be very good at not only searching, but to engage in a process that is sometimes called self-healing. The human role in this, I would argue, is primarily to train the machines to be self-healing. So let's get a little further into that. The idea of a self-healing grid has a historical initiative well before the beginning of the 21st century. It began in the US, at least, with the Electric Power Research Institute and the Department of Defense. And they developed this ultimately into something called the IntelliGrid, and then they eventually called it the smart grid. And we're all getting smart grid in our homes if we haven't already, but also large amounts of the grid are becoming smarter. There's a related initiative that started mostly at IBM called autonomic computing. It really started in the early 2000s. And with the goal of creating computer systems that manage themselves at a very high level, but the human role being to give them the ability to do that self-management. The motivation for autonomic computing was that large-scale systems had become too difficult for humans to configure and to maintain and tune. And so they had to become not only self-healing, but self-sustaining and self-protecting. And in other words, how do we make them sustainable? And in particular, coming back to the grid application, how do we make a sustainable grid? So there's massive amounts of data that will enable us to make a sustainable grid. We do what are called phasor measurements. They measure the measurements for current and voltage. They measure the amplitude and the phase. And I think it's fair to say that my colleagues in the Department of Energy say that by now we can do MRI quality evaluations of the power system, and in particular of the visibility of an MRI. So traditional SCADA systems give you information like voltages and transformer flows and the status of breakers every 2 to 4 seconds. That's the key point I want to make. That's the traditional supervisory control and data acquisition measurement. Nowadays, with modern phasor technology, the measurements can be taken many times a second. So instead of every 2 or 4 seconds, there may be as many as 120 measurements in 1 second. So several orders of magnitude faster. It's so fast that human operators are not going to be able to sense an anomaly that fast. or take corrective action that fast when the speed of the corrective action is required. So we need new algorithmic methods to understand, process, and visualize data and find anomalies rapidly and do something about them. So the issue for grid robustness or sustainability is to design control procedures so the grid can quickly and efficiently respond when there's a disruption and be restored to essentially its normal healthy state. The algorithms that we need have to be able to respond to detected problems in principle without human input. They have to be able to handle multiple possible solutions and pick the best one. And they have to be able to understand what to do if none of the solutions is really good, which is an interesting twist. So you have to be able to efficiently monitor and probe the system. You'd like to stay ahead of it by making statistical predictions of impending problems. You'd like to automate the selection of probes and automate the learning of corrective actions. So where does the human operator come in? When should they have control or approval over machine-generated responses? It's the kind of thing we've been talking a lot about at this meeting, and it's certainly true, and especially true in situations like the power grid, where it's likely impossible for humans to play a role in the initial decision-making. So overall principle that we've been discussing applies especially to the power grid. When can a machine bypass the set of allowable responses that a human operator has given them? And that might arise in the case where there's no really good solution, as I mentioned before. So hopefully this sets the stage for the discussion. And I think rather than take questions here, I think we'll turn it over to Alexis or Dee, whoever wants to go next.
Okay. So I will say very few words about sustainability water management, no? Mainly in order to give you an idea of what are the type of problems that arise in water management and what it could be a different perspective when we talk about sustainability, no? Okay, let's start with the problems, no? Now, when we talk about water, first of all, we need to understand what water we are talking about, no? There is groundwater, no, which is what we found under the surface, no, in water fields, in aquifers, no, which is what we usually use for drinking purposes. We have surface water, which is essentially rain and snow, no. But then, besides this fresh water which we have around us, we have salt water, which is much more than the fresh water, because we have plenty of sea around us, which is salt water, no? And then we have wastewater, no, which is what we produce as a result of our human activities, houses, industry, agriculture, whatever, no? Now, all this needs to be managed, no? So when we talk about managing water, means have an idea of what does it mean managing all these different type of resources that are used for different purposes, no? And that integrates among them, and we will see very soon why this becomes important if we see the water as a system, no? Why that? Because water, no, transforms from one state to another one, no? So groundwater is pumped outside, is irrigated, no, or ends to the sea, then it evaporates, it becomes surface water, which ends to be groundwater, etc., etc. No, or it becomes wastewater, which ends to the sea, and etc., etc. So there is a continuous recycling of this water. No, now, what are the facts we observe? No, first of all, we have an overexploitation of groundwater. No, which means that we pump too much water, and we do that essentially in places where groundwater is not that much. For instance, in Africa. Now, what is the consequence of consuming too much groundwater? Is poor quality of water, because most of the times, as the aquifer goes down, gets infiltrated by the sea, which means that we mix fresh water with salt water. And the result is that we irrigate the agriculture, which needs fresh water, with salt water. And this is a disaster. No? This also has other cascade effects, as Fred was talking about the electrical, about the power grid, has other cascade effects, no, in the system. No. The other thing is that we have a very inefficient water distribution system. No, because these some of the times have been geared or designed sometimes centuries ago, and we still keep these systems working. We have an increasing waste of surface water, no, and this happens because we do not maintain our wild areas, which are supposed to improve and increase the capacity of the land, the earth, to absorb water. So instead of absorbing water and make it in groundwater, we waste it. It goes rapidly away, creating floods. Part of the floods we observe is not due to an excessive waterfall or excessive rain, but to the fact that we are not able anymore, the earth is not able to absorb the rain as it used to be. Too much tar, too much cement, too much forest which is not maintained, so it doesn't absorb. No, so we create by ourselves the conditions for which what will naturally be rainfall becomes a flood, because water is not absorbed. And then there is a last point, which is mistrust in recycling water. No, so although there are very efficient systems on recycling wastewater, no, well, actually nobody wants to drink it, or almost, and nobody wants to irrigate his plants with recycled water, although in reality it would be very safe. No. Now, what is the problem behind that? No, the fact is that we increase the amount of water we use for industry, agriculture, drinking, and recreation, no, without considering the water a finite resource. Water is not as much as we want. We have a finite amount of water, but we keep increasing the amount of water we use. Why this happens? For instance, in agriculture, one of the reasons is that plants and agriculture, which consumes a lot of water, no, is much more profitable. No, so instead of producing, let's say, agricultural products which are, in quotes, dry, it's preferable to produce products that are full of water. Watermelons are much more profitable than apples or potatoes or onions. No? For instance, in agriculture, this as a result that we increase the amount of water that we are using. And there are other reasons for which there is a more than reasonable increase in the consumption of water. Now, in front of that, there are a number of issues. Let's call it the production of water, which is essentially raining, is totally uncertain. You don't know how much it will rain, when it will rain, where it will rain, etc. The consumption instead is constant. So you have a resource which is produced on a very variable way in front of a consumption which is steadily increasing. Water has no owners, but it is sold as if it was a property. This makes a very strange situation, because everybody feels that he owns part of the water where he stays, but at the same time, he's also ready to pay for buying water, as if water was property of somebody. So this fact that we don't have a clear definition of what the water is in terms of good, we generally consider water as being a common, but it is a peculiar common because we price it, which is not what we do for other commons. And last but not least, floods and droughts are increasingly frequent. This is related, as I said before, to the fact that it's not only due to the climate change. This is one of the reasons for which we have increasing floods and droughts, because we have an increasing variability to the production of water, but it is also due to the fact that we maintain badly the system that manages the water. And when I say badly, I mean really badly. The last example has been a disaster in a small island in Italy with people that has been killed, etc., etc. And clear the reason is bad maintenance of the infrastructure of the island. Now, what does it mean, sustainability? This is what is I try to describe what it means, let's say, managing the water, what type of problems we may have. Now, we need to establish a systemic view of what water is, and what does it mean managing it, which means that we need to have a clear idea of how the system, the components of the system interact. So what happens with the water as it gets transformed from groundwater to surface water to salt water to rain and back again, where the water moves, how it moves, etc., etc. We need to have an idea, and the representation of that system is really complicated. The other thing is that we need to know what are the values the stakeholders that are involved with the water management have. We have to know, what do we know about water? Now, Nicola did a PhD about information sharing, showing that it's not that immediate that any type of information sharing will improve the management of the water resource. So we need to think, what is the information we need to share and for which purpose? So giving everybody any type of information about the water is such a mess. So we need to choose what are we sharing and for which purpose, no? And that was one of the clear messages of Nico's PhD, no? And then the last thing is that we need to design, no, how this system will evolve, no, staying out of the box, no? So trying to think configurations of the system about the water, no, which is not what we are used to, no? So we need to think about totally new ways of consuming water, no? Just to be provocative, because I have been nasty in the morning, I will be, no? What about stopping having a shower every day and having only once a week, for instance? No? Are you ready to smell the humanity after 1 week not having shower? And are you ready to pay for that in order to have more water? Just, I told you, it's a provocation, but no, this is because I didn't have a shower yesterday, so I try. Now, let me conclude on that. No, we also need, in order to do that, no, to have a vision. No, now, Fred, when was talking about the electric grid, said the electric grid as it is, no, most of the times when it is disrupted, needs to come back as near as possible to what it was, no, which is more or less what we call a resilient system. No. Now, with water, perhaps we need to think in terms instead of anti-fragility, which is each time we have a disruption, how we can change the system so that to improve it. No? So after we had a flood, after we have seen that that type of infrastructure that we built around a town or a land or whatever, you know, had the dramatic consequences we have observed. No, what about not rebuilding them and deciding to introduce something different on how this resource, all the infrastructures around it should be constructed? No, which is what regional planners and urbanists call anti-fragile planning, no? So something that will not only resist to some extent to these extreme events, but will recover better than what it was before the disruption. And that's it. Dee, you have the floor now.
Okay, so while that's going on, I can start actually. Yeah. So while that's happening, I just wanted to say hi, I'm Delia Pembrey, if you haven't met me already. And I would like to begin today by acknowledging the traditional custodians of the lands on which we meet today. And that's any land that we meet today, wherever we are in the world. And I pay those respects to their elders, past and present. And I extend that respect to any Aboriginal and Torres Strait Islander peoples that are here today. So the aim of this, first of all, I'd like to say thank you to Liz for inviting me to this workshop, and for Alexis and Fred for allowing me to jump onto their bandwagon and take a chance on this crazy presentation I'll probably give you. And this, the aim of this session was, I was invited to find examples of issues and disruptions involving sustainability when machines have a central role in addressing them. And to also find examples about where there is a human element, like who is affected by disruption, who is affected by the solution, is there an element of fairness, ethics in evaluating solutions, and whose values are taken into account. Now, over the past 2 days, there's been a lot of talk about values, and then some talk about ethics and fairness. So, but in this session, we'll be looking at bushfires. But the bushfire element is only just to get us thinking. I'll be introducing to you the boundary triage, and the boundary triage is my thesis work.
Yeah, well, let me call it up. Come on.
Yeah.
Try that.
Yeah. That's good. So in this session, I'm just going to be introducing to the boundary triage. And the boundary triage is only one component of the thesis. The boundary triage is something that talks explicitly about how boundaries come about through embodied ignition. And it does use, the objects, and it's also got heuristics. We won't be touching upon that today. But the main aim is to empower individuals and groups to reveal values at the boundary, from the aesthetic to the numerical, so that we can bridge that gap between those who are feeling the world and those engineers who look at the world with lots of numbers. And so and in this way, we can basically start to navigate the world. That can just tick. I know. Okay. So let's just getting on to bushfires, and essentially in 2019, 2020, we had in Australia we had bushfires. They were absolutely devastating. But we had a connected world, a seamless human-machine collaboration experience. Through social media, we were able to get messages out onto the world, and a lot of money came through. That's the machine component. We also, the machines were connecting human systems from financial institutions, government agencies, emergency and defense institutions, academia, education, and even those communities that we don't normally see were coming online via social media. Sorry, I get a little bit emotional. Sorry. But it was a really tough time. And that was one of the things that we saw, that the machine component could actually help. What we're seeing in America also suffered the following year. And we're now beginning to see robots and drones and, mobile fire hydrants that are there to support, our emergency services. But it's more than that. We've got to be more than just looking at the emergency. We've got to be anticipating that emergency. We've got to be learning. And we haven't, if you type in wildfire monitoring, I've only just picked up 4, but there's actually quite a lot more. And there's a lot of data out there that is telling us about the current situation of wildfires and where they are. But is that data fully accurate? Can these systems talk to one another? These data systems that are picking up and sensing. Do they have the prediction capabilities? And what about the humans? Now, we also have emerging technologies. I touched on drones and robotic dogs before. We've also got satellites and digital twins, the artificial intelligence, which are components within digital twins or other systems, machine learning, and potentially quantum technologies in the future. But one of the things that we need to understand about human-machine collaboration, especially in the context of bushfires, is what do we mean from that? it's not just human machine and it stops. There's a variety of combinations. Like there's human machine human collaboration, which we can have, social media, which can give us collective action or misinformation. We can have human machine collaboration, where we're touching upon things like collective intelligence, open innovation. The human machine component is like, let's say you've got the satellite systems coming in, and then it comes down to a controller into the control rooms, and then it goes back into the machine again. So to basically coordinate on the ground level. And then we have like machine human collaboration. So this is where we might have a sensory system that is picking up information on the ground. It goes up to the cloud, and it comes back down, and we've got that human collaboration. Okay, so we've got all these different ways of configuring human machine collaboration. But where my focus is the fact that these are all of our creations, and in my journey, there was a senior army officer, and I think who was it that was doing some research with artificial intelligence and understanding the boundaries. But what they have a almost like a moral question, is that sometimes when they're using their artificial intelligence systems and their surveillance system, is that they have difficulty reminding themselves that behind every dot and every number that is going through our artificial intelligence systems is a person living their lives with family, friends, problems, and joys. And we often forget that when we're building out these systems. And I think that that's actually a key point when we are thinking about sustainability and resilience. And connections are critical for success, but they also reveal the greatest boundaries that have systemic impacts. So again, yes, we're connecting, but if we don't understand one another, if we can't communicate, or we misinterpret the message, so we start to get noise in the system, they actually have really bad systemic effects. And it's a known thing in design. I think in design circles, we say, okay, this is the design. And then when it turns out on the other side, it's exactly, not what you expected. So where I work, I work in a very large Australian government agency, and where it's situated is in the heart of, IT world. Everything you can think of it is like the machine, it's the pulse. But one of the things that we learned over the pandemic, and it's not just, the experience, but also in the research as well, is scale. When we understand time and scale, we begin to understand and acknowledge that our perceptions and how we start to design solutions must change as we move through that life cycle. As we go from the beginning where there's lots of ideas, and then as it keeps on moving down that life cycle to when we design, we develop, we test, and that's an area that we really need to get a hold of, is that testing space, because we need to embed ethics there, and then into the deploy. And as we deploy, we're going to start hitting out on more boundaries. And we need to be continuing to monitor for these systemic impacts. Leadership is key for every single one of us here, and from wherever it is. So to allow people to identify those areas where, to be able to speak out if they see that there is something wrong, and appreciating value systems from the aesthetic to the numerical. So I'm just going to keep moving here. So one of the things that the two disciplines that I work from are like critical systems thinking, because it then ties in with looking from it's touching on the anti-fragility. But critical systems thinking tries to look for improvement as well as emancipation from a system. It recognizes the plurality of systems, And this is Mike Jackson's Systems of Systems methodologies, which I really like, because it looks at the hard systems thinking, soft systems thinking, and the emancipatory systems thinking. It looks at simple and the complex. And we could look at them in isolation, but actually they're all occurring at the same time. And sometimes when we move into groups and circles and we're looking at transdisciplinary, multidisciplinary work, we need to appreciate where people are sitting within that space. Are you an engineer and you've got your hard systems thinking? Are you thinking on the simple side, or are you thinking in the mega project side? Okay. In the soft systems side, are you thinking about policy? Are you thinking about HR? What are these components? How are they going to influence that system? And the other thing as well, when we start to understand this, when we start to understand, you know, that there's a lot of people in there, we're all networked, but we've also got lots of boundaries. So how do we get that right spark to make sure that everything is happening? Now, I did actually put these slides through just to sort of show that there's also a range of hard to soft to systems and multiplexes of systems when we're looking at the machine. So we're part of the machine. We are the machine. So now I'm going to dive into like the boundary. What is a boundary? What I'd like to introduce is the idea of the boundary as a membrane or a gateway, so that it's a layer and it's a both and. It's dual and it's paradoxical. It's autonomous and it's dependent. It's keeping things in, it's keeping things out. You know, you can have an external pushing down, and you can also have an internal trying to emerge out of the boundary of the system. It can expand, it can contract, we can let things in, we can let things out. And this is really important to sort of like get that your head understanding that a boundary is not a constraint. It can also be part of a flow. And in cybernetics, when we observe boundaries, we can either look at it as something that's subjective. So I'm the observer observing that object, which is the first order, or I could be doing the second order, which is observing my thinking. So thinking about thinking, understanding how those boundaries are actually being created. Why am I deciding that that boundary is a boundary? Is it actually a real boundary? Or is it just one that is a perceptual boundary? And when we're designing solutions and scenarios and models, we have a responsibility to start thinking, who and what might we harm? When, where, how, and why? That is the ultimate question. Why are we doing what we're doing? And so this is the boundary triage. This is the simple form. And so it's sort of like the ABC of boundary, and it's an ontology and an epistemology at the same time. So the plus and minus is basically the B is describing what the boundary is. It's used to symbolize the simultaneously dual paradoxical nature of the boundary in question. Now, how do the boundaries come about? I'm now going to use the pictorials. Oh. Sorry, there's the boundary. So what I started to appreciate and understand is that every boundary that we know as beings, human beings, is that there is always one creator. It's going to be a human creator, and there's always only one. And then we have the acceptors of a boundary. And that could be me or you. Like when we're sitting, you're sitting here right now, and if you accept what I'm saying, you've accepted the boundary concept. And it also addresses, you know, anything like, you know, politics and that sort of arrangement. Then we have the reinforcing factors. Now that's everything else. That's all of our artificial intelligence. There's all our paradigms. That's our cultures. That's our influences. That's our values. Those are all our values. You know, It could be fiscal, it could be cultural, it could be aesthetic, it could be pain even. And all of this feeds into our decisions about how we view sustainability, how we're going to design around it. And what I'm asking is, when we get into a group, and this is what we need to start thinking now as we start to scale out artificial systems and machine systems, that we need to listen to each other's methodologies, because they're all going to be able to contribute to something greater. I've been in cybernetics, and often the majority of the time it's meant to be control and communication. And the communication component always seems to be missing for me. And that's the focus that I want to sort of like, you know, hone in, because it's through communication that we're going to be able to transcend those boundaries. It's where we're going to get the collective intelligence, and that's where we're also going to get that open innovation. And it's also how we're going to be able to respond to any crises so that we can get to that resilient state. And now the final thing that I want to say is that there is an autopoietic function in this boundary triage. And that is when you become an acceptor, so you're listening to information from me, and if you accept what I'm saying, then you become a creator in your own mind, because in your mind, you're making an association, right? You're making an association with the words that I'm saying, the visuals of this room, the environment, and that's, you know, and that's how you get this bounded object. That's how you get your memory. That's how you get your idea. And that will then start to systemically move forward in time. So, yes. And a note on the reinforcing factors. The reinforcing factors can be moved up and down. They're negative and positive. So they're the adverse, you know, a negative, you know, when I say negative, what I mean is like, if you don't agree with something, it goes into that reinforcing factor and it decreases your value system. So you might agree with something one time, but then you'll get a lot of events that will occur or people saying things. And next thing you know, you don't agree with that statement anymore. And this is actually very important when you're talking about policies, because especially in policy development, we need to be able to maneuver around and navigate when the environment is changing or the experience is changing or society is changing. What do we need to change? How can we change it? How can we change those boundary objects so that we can then start to act in the world and be sustainable? So that's the end. But in terms of like, how does that fit in with machine, you know, human machine collaboration? Thing is, we're the ones that are creating the machines. And from what I'm hearing is that the machines are not, you know, we're having difficulty collaborating with the machines, and the machines are having difficulty collaborating with us. So maybe what we need to do is start to understand how we communicate and collaborate to be able to build that into the artificial intelligence and into the machines that we are creating. Thank you.